class. Happy Monday, last week of class. So today we're going to continue our discussion about reaction dynamics, actually thinking through microscopically and with principles of statistical mechanics, how we can describe chemical reactions. And we ended up last week with a really exciting and really foundational result used throughout physical chemistry, used throughout chemistry in general. And that was the so-called transition state theory, which actually let us estimate the rate of some chemical reaction. So let's remind ourselves a little bit about that result first, before we then kind of expand our description about reaction dynamics. So what we had in mind was if we had some reactant A that was going to react to form some product B, that in general, if that reaction is a bond making or breaking reaction, even some isomerization process, that typically it's slow on molecular timescales. The kind of basic unit of times for molecules are the times over which they move short distances or times in which they vibrate or rotate. Those are all on the order of a picosecond. A typical reaction is going to be an infinitely long or nearly infinitely long time relative to that picosecond. It's millions of times that fundamental time unit. So even something which occurs on a microsecond, which to us is of course very fast, from the perspective of a molecule is a really slow process. So we reminded ourselves that a reaction, that rate of going from A to B was small. The time scale of that reaction was long, not because molecules move slowly as they go from A to B, but rather they have to wait for a sufficiently long time so as to see a sufficiently rare fluctuation occur. So what we envisioned was that if we had some coordinate C, which is some reaction coordinate, something that distinguishes reactants A from products B, that if A and B are long-lived, if they are metastable, they have sufficiently long lifetimes, then necessarily separating A from B must be a barrier. So maybe the reversible work to go from A to B by moving this reaction coordinate would look something like this. Let's clean this up. That's not very pretty. Oof, even worse. All right, that'll have to suffice. So we have a reactant base in A, a product base in B, and separating those two with some barrier we called the transition state, the place where the system has to wait for a fluctuation to take it between A and B. And when viewed from this perspective, that why rates or chemical reactions are slow is because they have to wait for that rare fluctuation. Well, we know, using the tools of statistical mechanics, how likely one of those fluctuations would be. Those would just be given by that Boltzmann factor associated with that reversible work. And so using that basic insight and doing some accounting for how often then a molecule is likely to go through that transition state, we ended up with an estimate of the rate of A to B, so-called transition state theory rate estimate, which was just the probability to have that rare fluctuation, provided the system starts in A, so that's a relative probability for getting to that transition state, given you start somewhere in the reactant basin, times the flux over that transition state, which is just given by some average velocity, divided by 2, because we only count fluxes that go in the right direction from A to B. So that transition state theory estimate then is just a product of the likelihood to see that rare fluctuation times the rate at which you would go over that barrier. And I think we concluded last time by noting the temperature dependence that's predicted from this transition state theory estimate, which is that we know a typical velocity is going to be proportional to the square root of the temperature from Maxwell-Boltzmann statistics. And if the barrier height, the change in reversible work to get to that transition state, has a large energetic part, then we should expect that that rate is going to be proportional to the square root temperature dependence is going to be negligible relative to the exponential temperature dependence we would expect from having a large energetic, let's give that a delta E, large energetic part of that barrier. And indeed, this is then the same form that we've learned long ago, the so-called Arrhenius law. That says that a rate has some prefactor and is exponentially suppressed and some activation energy. We see how that comes out naturally from a statistical mechanics, whereby that exponential is just due to the rare fluctuation we have to wait for to have happen. Now, this perspective is a little incomplete in the sense that we have judiciously imagined that we can identify a reaction coordinate that tells us the most dynamically meaningful motions that contribute to a reaction. You might wonder how we can incorporate information about, say, other coordinates. So if we imagine this reversible work surface, in principle, could extend in some other dimension. And shouldn't those coordinates play an active role in some dynamics that takes the system from A to B? This transition state theory result is seductively simple. It has just thermodynamic quantities in it. It has abstracted all of the kinetics we might imagine complicate a description of this process. If we go back to just our isomerization of that cyano group, so we have some, say, acetonitrile that can isomerize. Well, the reaction coordinate might be the rotation of that cyano group. But equally importantly, might be, say, some distance over which the carbons extend. There could be lots of other coordinates which might play a role. And have we in any way taken those into account? If we're actually thinking about dynamics which move those atoms around, shouldn't we have to worry about all of those coordinates? Well, in this discussion requires a little bit of nuance. In some sense, we have included those coordinates. The exponential factor, that reversible work factor, we know is proportional to a partition function where I've fixed that value of the reaction coordinate. Now that partition function is necessarily a summation over all other coordinates. Namely, if I was going to try to compute that partition function, I would take the Boltzmann weight of some microstates, and I would sum over microstates with some fixed value of that reaction coordinate, but that necessarily means that I sum over all other coordinates that are not being fixed. So in some sense, implicit in that Boltzmann factor is a consideration of those other coordinates. The total reversible work, the total free energy to change the tagged reaction coordinate, this C, depends on those other coordinates implicitly through that sum. I've added up the contributions to all of those, to that free energy due to all of those configurations consistent with all other coordinates being every other value they can take. So the dependence on the other coordinates is implicit in our K. So for example, if I had, say, some free energy as a function of those two parameters in the isomerization of acetonitrile, let's try to draw that schematically. So I have some free energy as a function of that X, maybe that carbon-carbon bond distance, and that rotational angle. So if I was going to try to draw this function, well, this was my original reaction coordinate. Maybe this is that X direction. So I know that at some large value of that angle, say 180, I would have that basin associated with the isocyanide over at some small value of that angle, I would have the acetonitrile. And in these two dimensions, then I have some surface that has extent and features in both that X and C direction. Not the simplest thing to draw, but I think you can get the idea. So in fixing that specific reaction coordinate, C, I've summed over all other coordinates, like this coordinate X, and included those just in their equilibrium contribution to that C value, to that reaction coordinate. So here's my little A basin, here's my B basin. I've added up their contributions to the equilibrium weight. But what I haven't done is I've not included the potential for any meaningful dynamics to happen in those other coordinates. That is to say that if I really needed to worry about the flux in those other coordinates, how those other coordinates move or change in time in some non-equilibrium manner, in some way that's not represented just by knowing their equilibrium weights, their equilibrium Boltzmann constants, then I would be missing something in that estimate of the rate. The transition state estimate is really good if we have chosen the right reaction coordinate, but if we have neglected coordinates that are important to that reaction coordinate is not going to, that transition state estimate is not going to give us a very good description. You know, very generally away from transition state theory, the description of reaction kinetics and reaction dynamics is very complicated because a complete description is dynamical. And would require attention to all of the coordinates, which could be, for example, summarized by knowing a whole potential energy function. So that's a function of the two variables we've written down so far, as well as all other potential variables. If I really want to know in detail how that reaction proceeds, I really need a lot of information from that. Say if I was imagining things happening classically, from that potential energy, I could, through Newton's equations, relate the potential to a set of forces. From that set of forces, and knowing that F is equal to ma, I could then get the complete time dependence of any set of coordinates. But to know that time dependence requires knowing those forces in the full dimensional space of whatever that potential energy is specified in. That is to say that if I was going to imagine a trajectory that starts in A, you know, how it moved around to B, how I would dynamically evolve that time series would require a full potential energy surface, not just some reduced dimensionality space. Transition state theory is amazing in that it can provide useful estimates of a rate without that information, but it requires tremendous insight into knowing what the right reaction coordinate is. So I want to talk a little bit about a specific case where the dimensionality is small enough that we can, in a significant amount of detail, think through the reaction dynamics completely. That is, we can write out or sketch out a model for the full potential energy surface and think through how the reaction then proceeds on that potential energy surface. So the remainder of our lecture today will be focused on a specific example. That is itself pretty simple. It's essentially the simplest reaction you can ever imagine studying, and that's the exchange of a hydrogen between its monatomic form and its gaseous form. So some H prime adding to H2 and exchanging that hydrogen. Now that is a a reaction, not a very exciting one, but a reaction. Nevertheless, I have to break a hydrogen-hydrogen bond and reform a different hydrogen-hydrogen bond. And it is completely specified by two coordinates. If we imagine this happens on a line. So in a tube, we're imagining that H2 can't rotate. It has to move translationally with a fixed angle. In such a arbitrarily constructed case, there are only two relevant coordinates. A distance 1, which will be the distance from the incoming hydrogen to the molecule, the hydrogen that it's going to bond with, and a distance, let's give that a double prime, a distance d2 between the molecule that's formed and the hydrogen that is leaving. Now, these two are sufficient because we don't have to worry about, for example, the center of mass of all three species. So these three atoms moving on a line have three spatial coordinates associated with them. To specify the dynamics of this reaction, however, we require only two, because that if I translate the whole center of mass of all three to some new point in space, I haven't changed how those three atoms interact with each other. So what we're going to try to work through or reason through is how this reaction might proceed. What would the dynamics over which this hydrogen exchange occurs with? And to do that, as I've already alluded to, we need to think through the potential energy surface, or what the potential energy surface in these two coordinates looks like. Because as before, if we know the potential energy surface, we could in principle compute forces, and from those forces propagate the system in time. Now, before we get there, I want to take a second to prime you all a little bit with a refresher on dynamics on potential energy surfaces. You probably haven't really thought about this much since a mechanics class you took maybe your freshman year or so. Okay, so let's take a little bit of an aside to think through dynamics generally on potential energy surfaces. So let's imagine we have some simple coordinate x. And say, imagine we have a potential defined on that x, a potential energy which varies with x, which is just harmonic. Something looks like that. So if we were going to sketch out that potential energy as a function of x, it would just look like that. Right? So now if we were going to imagine how a ball bearing moved on that potential energy surface. So we have some ball, if we're going to place it there, say at some height on that surface, what would the subsequent motion look like? If we were going to follow say, the x direction in time. Do you all remember what that would look like? So if we took that ball bearing, we pulled it up to that point x prime, say minus x prime, and let it go, what we would see is that the ball would drop. Kinetic would then get, that potential would get turned into kinetic, bringing that ball up to some point, and then that ball would then subsequently fall back down. So I'd have some initial decrease in x as it moved towards the minimum of the potential before it increased up, and then that, because of conservation of energy, would fluctuate about forever. So if we had a minus x prime and a plus x prime, Newton's equations would be solved and give us something that moves around periodic like so. Hopefully you all remember how that kind of proceeds. Now, what if we had, let's increase the complexity a little bit, and we had now to consider two coordinates. Both of which are periodic, or both of which are harmonic. So we have some potential energy defined as a function of both of them, which is just a sum of a harmonic in that x1 and a harmonic in that x2. Something look like that. So if we were then going to draw out the potential energy surface, it is now a surface. It's a function of both x1 and x2. Rises up in that direction, rises up in this direction. Look something like so. My best interpretation of a 3D rendering of what the surface would look like. So these lines are lines of constant potential. So that is a line with u equals u1, for example. This line would be a line of constant u is equal to u2. So that's a simple way of, say, presents us with another simple way of representing that potential, say, as a contour plot. I could try to draw that in 3 dimensions like I have before, or I could draw this kind of parametrically in x1 and x2 with lines of constant, lines of constant potential. So here's that line of constant potential u1. Here's a line of constant potential u2. Okay. There are many such lines. Right, so that's 2 different representations. The contour plot is a little more useful of a representation when we move to these 2-dimensional surfaces than just the parametric representation of x is equal to y is equal to x when we have a 1-dimensional surface. And we could imagine dynamics, especially simply when superimposed on that contour plot. So for example, if I was going to start that ball rolling now in this two-dimensional potential surface with some, say I don't even have an initial velocity, I will again have some periodic dynamics that returns me back to that initial point because of conservation of energy. So I might, for example, initially decrease in x1 and x2, passing back through the origin before increasing in x2 and moving about that continuously. So that red line, for example, might be an example trajectory that a ball bearing would fill if you pushed it around on this potential surface. Okay, so that gives us enough insight then to launch ourselves into our H plus H2 reaction. Okay, so if we're going to try to construct our potential surface for this reaction, I'm going to try to do it in a couple steps. So let's first try to envision what the potential energy surface, again, we're defining it with these variables d1 and d2. Let's put d2 over here. So let's try to work out what that potential surface might look like. So for the reactant state, when d1 is much, much greater than d2, again, d1, if we mind ourselves up here, was when that incoming hydrogen H prime was d1 is the separation distance between that incoming hydrogen H prime and the H2 molecule. So when that incoming hydrogen is very far away, we would imagine that D2, the bond distance, bond length between the existing H2 molecule, is going to oscillate around some equilibrium position. So you all probably know what the bond length, the average bond length or bond distance between a hydrogen-hydrogen bond is, pretty close to an angstrom. So when when that incoming H prime atom is very far away, H2 is going to vibrate just like it normally would with some equilibrium bond distance, and it's going to be insensitive to the specific value of D1. So a reasonable form for the potential in this limit would be some number plus a description of D2 harmonically oscillating around that equilibrium bond length, like so. So if we were going to try to draw that, let's say that this is our value of that equilibrium bond length. At large values of D1, we're going to have some harmonic function, and this is going to extend in a way that's insensitive to D1. So just as a function that looks constant with respect to d1. Let's do this in another color. Okay, so something like that, where this value of the minimum relative to whatever the floor is our u naught, right? Now, what about when we're far into the product state? Namely, when d2 is much, much greater than d1. Well, we're going to imagine having the exact same thing, right? If d2 is much, much greater than d1, then that means that locally that d2 variable is not going to be important. So d1 would oscillate like a harmonic oscillator about some H2 bond average distance. And so we can imagine that, especially if these are the same kind of hydrogens, they really are hydrogens, not deuteriums, not anything else, not anything that would change the bond strength, that you'd have the same potential offset and the same characteristic stiffness of that harmonic oscillator, now just about D2 or D1, excuse me. So again, if we were to draw this, now the potential in the limit that D2 is large, you'd have some equilibrium distance. Let's do this in blue again. So the potential in that limit would look something like this, right? Just as we had before, just rotated about for the product state. Okay, now what about the transition state? What is the high energy fluctuation that we have to have happen in this two-dimensional surface? So that's when D1 is pretty close to D2. We have our H prime and our H double prime. Now both of those bonds are going to be stretched. The H in the middle is somewhere in between. And because both of those bonds are stretched, the energy is going to be higher in that region. And we'd imagine that the potential surface depends on both of those in some complicated way, right? We can't say that D1 is going to change independently of D2 anymore. So first, U is sensitive to both. We'd expect that the U in this region is much greater than that value far into the reactants or product states. And so if we try to give this a draw, so we'll have some potential. We have an extension of D1, extension of D2. We had our harmonic potentials for those reactants and products. Now this has to be some continuous function. So first we'll imagine that energy increases. It is symmetric, both of those states are the same, deep into the product state or deep into the reactant state. So maybe that surface looks something like this. So there's our offset for D bar. Oops, sorry. Here's our offset for D bar into the product state. We have some contour lines we could draw, constant values of U, the potential. And they would look something like that. Yeah. Let's even get some fancy shading in here. Oh, that's going to be too big. All right, so this is probably a pretty reasonable cartoon of what that surface might look like. And again, it's the same going out to the products or into the reactants. It has some transition state region over here. Let's go back to black. Transition state region where D1 is pretty close to D2, which increases that energy. So here's our transition state. We have our reactants that live out here. We have our products that live out here. And now that transition state, if we tried to imagine a trajectory whereby that H prime molecule comes in, it indeed has to have a rare fluctuation to bring it up in energy and over that transition state, a saddle point that's centered on that inflection, a point at which I have a negative derivative in one direction and a positive derivative in the other direction. That's what a saddle point is. And that's where the transition state is located. Okay, so that's in 3 dimensions what that surface might look like. Again, if we wanted to actually try to draw some dynamical trajectories of this process, it'll be simpler to do it on a contour plot. So let's put D2 over here. D1 over here. In this plane, I have symmetry about D1 goes to D2. I have my reactant channel, product channel. Those are locally harmonic. If I was going to draw contour lines, it would look like this. And now let's draw that saddle point. something like so. All right, so that's a contour plot. So let's imagine now we send in that H prime. What's going to happen? Well, there's a couple of things that could happen, right? We could imagine that H prime comes in. It's got some velocity, presumably in the d1 direction. d2 probably has some velocity too, so we could draw some periodic trajectory, and maybe that trajectory might look like that. If it had sufficient energy to overcome that barrier, you would indeed see a reactive trajectory. I'm going to do something clever here. I'm going to actually take a copy of this. Then I have to drop, oh shit. Try that again. Copy. Let's redraw that trajectory. Something like so. So that would be an example of a reactive trajectory. That H prime comes in with sufficient energy that it can overcome that barrier. We could also imagine an example where that H prime comes in with insufficient energy to overcome that barrier. So let's give it a blue color. So maybe a non-reactive trajectory might look like that. The H prime coming in with not enough energy to overcome the saddle point to actually react. So those are two possibilities for what happens when that H prime comes in. It can either come in with sufficient energy to overcome that barrier, come in with sufficiently little energy, in which case it would come some way up the hill, but then get kicked back out. So if we wanted to go back and think about, say, how we might estimate the rate of this process, well, again, we need to, transition state theory would tell us that all we need to do is find the likelihood or estimate the likelihood of getting up to that point, that saddle point in the potential energy surface. But transition state theory requires us to identify a single reaction coordinate. We don't really know how we would use both D1 and D2 in such a calculation. So maybe we could construct an idealization of some reactive trajectory and use that to inform what would be a reaction coordinate. So let's do this again. I can paste this image. So maybe if I looked at many examples of a reactive trajectory, each coming in with slightly different phase, with slightly different energies, on average, maybe a reactive trajectory looks like this. In which case, I could imagine parameterizing points on that curve with different values of some reaction coordinate. Let's say that that value has a value of the reaction coordinate C1. Maybe this value is C2. This, then, the location of that saddle point, would be the value of that reaction coordinate, which is the transition state. I could further parameterize that curve essentially at large D1 or large D2. That reaction coordinate looks just like one of those variables, just maintaining the progress of going out that reaction or product well. So this would be a way of, say, parameterizing the progress along this reaction. Which could be informed with this idealized average trajectory. If we were then going to try to write out what that reversible work surface would look like, well, the free energy as a function of that reaction coordinate would be flat at the extremes, with that bump in the middle right at the saddle point in that two-dimensional potential. So again, we could, just with transition state theory, ask for what the flux over that barrier is, and provided the height, we could estimate that reaction rate. Okay, so this is a little more nuanced discussion of chemical dynamics, reminding ourselves of the fact that a full dynamical description of some reaction really requires lots of information. If we really wanted to understand how a reaction proceeds, we need to think of a full potential energy surface and the dynamics that evolve on that surface. Transition state theory is a means of estimating the rate of some process, but it requires that we really know a lot about the mechanism by which it proceeds already, such that we can have kind of a idealization of the typical reactive trajectory in mind. So this little H plus H2 example was an example that we could use to get a lot of insight into how reactions proceed in that full dimensional space. Because it's a simple two-dimensional problem, we could write out what that full potential energy surface looked like and actually think about dynamics on that surface. And to that end, I would implore you all to download the Mathematica demonstration I'll upload to B courses, which actually implements Newtonian trajectories on this potential energy surface parameterized for a reaction like H plus H2. So here's what this would look like. Here's our 2D potential written in or plotted in a contour plot. And by giving the initial position and velocity of some particle, say changing it to have a larger initial velocity or a smaller initial velocity in different directions, this little Mathematica notebook will compute what that trajectory would look like. So you can see that how, for example, if you had lots of energy or a little amount of energy coming into that saddle points, you'll either get reflected back out or actually make your way over the barrier. So if we, for example, it's a little laggy, hopefully that'll show up in a second. Okay, so you'll be able to play with it on your own, but you'll be able to see different trajectories and how they depend on the initial energies that the H prime molecule comes in with. I implore you to go play around with that. I think it would give you some more insight into that kind of mechanics. Okay, all right, well, thank you all for your attention. And again, if you haven't already done so, please do fill out the evaluations. I take those very seriously, even in the unique situation we're in now. I think they would be useful to know how you all have thought the class has gone.